Welcome to Wisdom Docs. Somewhere in the north of Tanzania, where the land begins to crack and pull itself slowly apart, there is a mountain that does something no other mountain on Earth is willing to do. It pours out lava that is black. Not orange, not the searing gold you have seen in every photograph of an erupting volcano, not the river of fire that glows so brightly it hurts to look at. Black, dark and slow and quiet, moving across the ground in the daylight more like mud, or motor oil, or wet tar than like molten rock. And if you came back to that same spot the next morning, after the night had passed and the cool air had settled over the rift, you would find that the black flow had turned the color of dirty snow. Let that sit for a moment, the way you would let your head sink into the pillow. A volcano whose lava runs black and cold and then turns white while you sleep. This is Ol Doinyo Lengai, and tonight we are going to walk slowly down into its strangeness together. There is no hurry. Nothing here is going to startle you. The mountain itself is unhurried, the kind of place that has been doing what it does for a very long time, in its own quiet way, without asking anyone to watch. So we will match its pace. We will take the long way down into the chemistry and the legend and the slow geological breathing of the place. And if you drift off somewhere in the middle of it, that is perfectly all right. The mountain will still be here. The story does not need you awake to keep being true. The mountain stands in what geologists call the Gregory Rift, which is the eastern branch of the Great East African Rift System, a place where the very crust of the continent is slowly tearing itself in two. You can picture it like an enormous ancient seam in the skin of the earth, a line of weakness running for thousands of kilometers, where the land on either side is, almost imperceptibly, pulling away from itself. It is not fast. It is the slowest possible kind of violence, a few millimeters a year, the width of a fingernail's growth, the kind of motion you would never feel standing on it. But over millions of years, that patient pulling has opened valleys and lifted ridges and let the deep heat of the planet find its way closer to the surface than it usually dares. And in one particular spot along that seam, in northern Tanzania, not far from Lake Natron and within reach of the Serengeti and the great bowl of the Ngorongoro crater, the heat found a way out and built itself a mountain. It rises about 2,960 meters, which is somewhere near 9,700 feet, a steep and elegant cone, the classic shape a child would draw if you asked them to draw a volcano, a clean triangle against the sky. And that shape, that tidy textbook cone, is the first small thing about Ol Doinyo Lengai that does not quite add up, though we will come back to that. For now, just hold the picture. A steep, dark cone standing alone on a tearing plain, with the soda-pale flatness of Lake Natron to the north and the high golden grasslands all around. The first geologists who came to measure what was happening inside this mountain came expecting one thing and found another. They came carrying everything they knew about lava, all the hard-won understanding of how molten rock behaves, and the mountain set most of it gently aside. Here is what they knew, what anyone who studies volcanoes knows in their bones. Ordinary lava, the kind that pours out of Hawaii and Iceland and most of the fiery places on this planet, the kind we call basaltic lava, erupts at a tremendous heat, somewhere around 1100 to 1200 degrees Celsius. To put a human number on that, it is hot enough that the rock itself becomes a liquid that glows from within, the way the filament of an old light bulb glows, the way iron glows in a blacksmith's forge. It is so hot it makes its own light. That is why lava is orange, why it is gold, why it looks like a river of fire even at high noon. The heat is the light. The two are the same thing. So when researchers pushed their instruments toward the flows oozing out of Ol Doinyo Lengai and read the temperature, they read something that should not have been possible. around 500 to 600 degrees Celsius. The careful field measurements clustered even tighter than that, somewhere around 510 to 590 degrees, roughly half the temperature of ordinary lava, the coldest erupting lava ever measured anywhere on the surface of the Earth. And here is the thing about heat and light that explains the color. At 1100 degrees, rock glows bright, but drop the temperature down by half, and the glow drops away with it. 500 or 600 degrees is still hot enough to scorch, still hot enough to set wood on fire, still genuinely dangerous. But it is not hot enough to shine in daylight. The sun overhead simply washes out the faint glow it does produce. And so in the bright African afternoon, this lava emerges looking black, dark brown in places, almost the color of old tar, oozing and creeping and folding over itself, glistening a little but utterly without that inner fire we expect. Only at night, in the dark, when there is no sunlight to drown it out, does the flow reveal a dull, dim, sullen glow, a deep reddish-orange fare weaker than any normal lava, the embers of a fire that has mostly forgotten how to burn bright. Now I want to pause here because there is an obvious question forming, the same question the first scientists must have asked themselves as they stared at the readings. Is this even lava at all? Is this some trick, some imposter, some mud, or hot spring, or chemical sludge pretending to be a volcano? Because surely lava, by definition, is hot, molten rock. Surely something this cool, this black, this strange, cannot really be the same thing that builds the islands of the Pacific and the slopes of Vesuvius. And the answer, the genuinely astonishing answer, is yes, it is real lava. It is real molten rock, real magma, rising from deep inside the planet, erupting from a real volcano, along a real fault in the breaking continent. There is no trick. It behaves like lava because it is lava. It is simply made of something different. And that one difference, that single change in the recipe, is what breaks every rule we thought lava had to follow. Because Ol Doinyo Lengai does not make its lava out of the stuff that almost every other volcano on Earth uses, almost all the rock of the planet's crust, almost all the lava that has ever flowed, is built on silica. Silica is silicon and oxygen joined together, and it is the great backbone of ordinary rock. Sand is silica. Quartz is silica. Glass is silica. It is everywhere beneath your feet. And silica has a particular habit, a particular way of behaving when it melts that shapes everything about how normal lava acts. Picture, if you can, the way molten silica builds itself. Each little unit is a tiny pyramid, a silicon atom in the center with oxygen atoms at its corners, what scientists call a silica tetrahedron, and these tiny pyramids do not like to stay separate. As the melt cools, they reach out and link to one another, corner to corner, building longer and longer chains, then sheets, then sprawling tangled networks. The technical word for this linking up is polymerization, but you can picture it more simply. Imagine a great pot of cooling honey full of tiny burrs that catch and cling to each other, snagging and joining until the whole thing thickens into a sticky, dragging, reluctant mass. That clinging, that constant reaching out to link together is what makes ordinary lava thick and slow and resistant. It is also part of why it has to be so hot. You need tremendous heat to keep all those little pyramids from clinging, to keep the network loose enough to flow at all. The silica wants to set. The heat is what keeps it liquid. Take away the heat and the whole snagging network locks together into solid rock. So that is ordinary lava in a single picture. Hot because it has to be. Sticky because the silica clings to itself. Glowing because the heat that keeps it liquid is the same heat that makes it shine. Everything about it follows from that one ingredient. And Ol Doinyo Lengai simply does not use that ingredient. Its lava is not built on silica at all. It is built on carbonate. And to understand what that means, you do not need to leave your own kitchen, because the carbonates are a family of compounds you already know: sodium carbonate, potassium carbonate. These are cousins of the washing soda in your laundry cupboard, relatives of the baking soda in the cabinet behind the flour, the very same chemical family. The lava that pours out of this mountain is, in its bones, made of the kind of soda compounds you could buy in a shop. Not silica, not the backbone of ordinary rock, but the white, powdery stuff of cleaning and baking, melted and rising from miles below the ground. The scientific name for this kind of lava is carbonatite, and it is worth saying slowly because it is the heart of the whole story. Natro for sodium, carbonatite for the carbonate it is made of. Carbonatite, a lava of soda rather than stone. And Ol Doinyo Lengai is the only volcano on the entire planet that is currently erupting it, the only one. Every other active volcano on Earth, all of them, the thousands of them, are pouring out the ordinary silica-based rock. This single steep cone in Tanzania is alone in all the world. And the reason carbonate lava behaves so utterly differently comes down to that same matter of clinging and linking that defined the silica. Carbonate, you see, does not have the same eager habit of reaching out and joining into long networks. The carbonate ions sit in the melt without that constant snagging, without building those sprawling, tangled chains. There is almost no polymerization, almost none of that clinging. And without the clinging, two things follow, two consequences that flow directly from this one fact and that together explain almost everything strange about the mountain. The first consequence is the low temperature. Remember that silica needed enormous heat just to keep its clinging network loose enough to stay liquid. Carbonate has no such network to fight against. It does not need to be kept that hot to stay molten. It melts and stays liquid at a far, far lower temperature, only 500 or 600 degrees rather than 11 or 1200. The heat that ordinary lava must carry just to overcome its own stickiness, carbonate lava simply does not need. And so it comes out cool, and being cool it does not glow, and not glowing it appears black. The second consequence is the fluidity, which we will explore more deeply as we go, but you can already feel where it is heading. Without the silica's clinging network to thicken it, without all those tiny pyramids snagging on one another, the carbonate melt has almost nothing to slow it down. It is thin, it is runny. It flows not like the dragging, reluctant, slow-heaping ordinary lava you have seen creeping down a mountainside, but almost like water, almost like thin oil. It runs and spreads and pours in delicate, thin sheets where you would expect a thick, slow, piling tongue of rock. The same absence of clinging that makes it cool also makes it loose. The two strange properties are really the same strangeness wearing two faces. And so we begin to see the shape of the puzzle that drew people to this mountain in the first place, the cluster of things about it that simply should not be true at once. Nobody, looking at this mountain for the first time, would believe lava could be this cold. Nobody would believe a flow of rock could run black and dim in the daylight. And nobody quite agrees, even now, on every detail of how it comes to be. The mountain holds its strangeness gently, but it does not entirely give it up, because the truth is that Ol Doinyo Lengai does not break just one rule. It breaks 4 of them at once, quietly, all at the same time, the way a single quiet person might turn out to defy every expectation you had brought to them. It is too cold to glow. That is the first broken rule, the one we have just walked through. Lava is supposed to be a river of fire, and this lava is a river of cold, black mud. It is too runny to be rock. That is the second. Molten stone is supposed to be thick and slow and heavy, and this stuff flows nearly like water, spreading thin and quick across the crater floor. It is too unstable to survive as stone. That is the third, and we have not yet touched it. So let me only set it gently in place for now. A loop to be closed much later, the way you leave a door slightly open to come back through. The rock this lava cools into is so fragile, so easily dissolved, so quick to crumble and wash away, that it essentially cannot last in the ground. Almost nowhere on Earth do we find old nitrocarbonatite preserved in the rock record, because it erases itself. It does not survive, which makes this one living mountain a kind of window into something that has otherwise vanished from the world. But we will return to that. Hold it lightly for now. And the fourth broken rule is the strangest one of all to a scientist and the most human. This mountain is too sacred to be only science. Because Ol Doinyo Lengai is not merely a geological curiosity to the people who have lived in its shadow for generations. Its very name in the Ma language of the Maasai people means the mountain of God. To the Maasai, it is the dwelling place of their deity, and they have made pilgrimages to its slopes and prayed beneath it, and read in its two moods, its gentle face and its wrathful one, a mirror of the divine itself. We will sit with that meaning later, slowly and with care, because it deserves to be told properly and not as some quaint footnote. For now, it is enough to know that this is the fourth rule the mountain breaks. It refuses to be only a problem for chemistry to solve. It is also a holy place. And the remarkable thing, the thing worth keeping somewhere in the back of your drifting mind, is that the people who named it the Mountain of God may have understood its double nature, its two faces, more truly than the first geologists who flatly refused to believe lava could ever be this cold. So that is the shape of where we are going tonight. 4 broken rules and 1 quiet mountain. Too cold to glow, too runny to be rock, too unstable to survive as stone, too sacred to be only science. And we will take each of them in turn, slowly, in the dark, the way you would walk a familiar path by lamplight, in no hurry to reach the end. If you find this sort of slow wandering through the strange corners of the world is the kind of thing that helps you settle towards sleep, then I am glad you are here, and you are very welcome to stay. And while we are still near the beginning, before the deeper descent, I would love to know quietly where in the world you are listening from tonight. The high latitudes where it is already cold and dark, or somewhere warm with the windows open. Leave it in the comments if you feel like it, just a word, just a place. And if you are new to the Wisdom Docs, you are welcome to subscribe and drift back whenever you need a long, slow story to fall asleep inside. There is no pressure in any of it. The mountain does not mind either way, and neither do I. Now, let us go back to the lava itself and stay with it a while longer, because there is more to feel about the simple fact of its temperature before we move on, and feeling it slowly is the whole point. Think again about what 500 degrees actually is and what it is not. It is not the gentle warmth of a summer afternoon, not the heat of a kettle or an oven. It is genuinely fierce. It is far hotter than any oven you have ever owned, hot enough to ignite paper and wood and cloth in an instant, hot enough to do terrible harm. Do not let the word cold mislead you. Cold here is only relative, only cold compared to the 1100 degrees of ordinary lava. It is the difference between two kinds of furnace, not the difference between fire and ice. The mountain is calling something cold that would still kill you if you touched it. There is a lesson somewhere in that, in how the names we give things depend entirely on what we are comparing them to. To a stone from Hawaii, the lava of Lengai is astonishingly cool. To a human hand, it is death. Both things are true at once. The mountain seems to specialize in things that are two true things at once, and the blackness of it in daylight has a quality that the photographs never quite capture, that the people who have stood at the crater's edge describe almost in disbelief. They speak of expecting fire and finding instead something that looks more like the contents of a broken machine, like spilled oil, like dark slurry, oozing and folding and turning slowly over itself across the pale floor of the crater. It glistens, it moves. It is unmistakably liquid, unmistakably alive in the way that flowing lava is alive, but it has none of the drama we associate with eruptions, none of the roaring brightness. It is a quiet, dark, almost humble kind of flowing, the most undramatic lava on Earth, creeping black across the ground while the sun beats down and steals away what little glow it has. You would have to wait for night to see it for what it is. And even then, even in the full dark of the rift with no moon and no city light for 100 miles, even then the glow is faint. A dull red, a deep, weary orange, more like the last embers of a fire that has burned down low than like the white-hot heart of a furnace. You could look at it without your eyes hurting. You could watch it for a long time, that low and patient glow moving across the crater floor in the darkness, and it would never blaze, never flare, never blind you. It would just continue, quietly, the way some old things continue, the way the night itself continues, without ever needing to announce itself. And all of that, every bit of it, the blackness and the dimness and the cool, fierce heat, comes back to that single change in the recipe. Carbonate instead of silica. Soda instead of stone. The absence of all that clinging, all that snagging, all that reaching out to link into networks. Take away the silica's eager habit of joining to itself, and the lava no longer needs to be kept so hot to flow, and no longer being so hot it no longer glows, and no longer glowing it runs black in the day. One ingredient, one difference, and from it, like a thread pulled loose from a hem, the whole strange tapestry of the mountain begins to unravel into something no other place on Earth can show you. We have only just begun to follow that thread. We have seen why the lava is cool and why it is dark, and we have confirmed that it is genuinely lava and not some imposter, genuine molten rock rising from the deep heat of the breaking continent, only built from a different family of compounds than anything else that erupts on this planet. And we have laid out, like stones along a path, the 4 rules this quiet mountain breaks all at once. But we have not watched the most beautiful thing it does. We have not yet seen what happens to that black flow when the night passes and the morning comes and the air with all its hidden moisture goes to work on the cooling soda. We have not yet seen the black turn white. We have not yet seen the crater come to look as though it has been dusted with frost, with dirty snow, with salt, in a land where it never snows at all. That slow transformation, that quiet overnight change from dark to pale, is perhaps the strangest and gentlest thing this whole strange, gentle mountain has to offer. And it is exactly where we are heading next, down a little deeper, a little slower, into the chemistry of soda that drinks the very moisture out of the air. Before we go there, though, it is worth sitting for a moment with the simple fact of the temperature, because the number itself, once you let it settle into you, is harder to believe than any description of it. 500 degrees, maybe 600 at the warmest. And against that, the ordinary lava of the rest of the world, the lava we have all seen in photographs and films, the rivers of orange and gold pouring down the flanks of Hawaii or Iceland, glowing so fiercely you cannot look at them without squinting. Those run at 1100, 1200 degrees and more, twice as hot, more than twice sometimes. So that this lava, the lava of the mountain of God, is not a little cooler than normal lava. It is not the low end of some ordinary range. It is half. It is a thing that erupts at roughly half the temperature that lava is supposed to need, and that single comparison, 1100 against 500, is the whole reason scientists could not, at first, bring themselves to believe what they were seeing. Imagine being the first to measure it. Imagine carrying your instruments up the steep cone of an unfamiliar mountain in northern Tanzania up into the Gregory Rift, where the continent itself is slowly pulling apart, and standing at the edge of a crater where black liquid is moving like oil across the floor, and lowering your measure into it, expecting the great heat that lava always carries, the heat that drives you back, the heat that ruins the very tools you are trying to use. And finding instead a number so low you assume the instrument is broken. You check it again, you check it a third time, and the number holds. The man whose name is tied most closely to those first careful descriptions, J.B. Dawson, the geologist who set down the early science of this place, gave the world a fact it was not ready for, that there was a volcano erupting lava barely hotter than a kitchen oven set to roast, lava you could feel the warmth of from a distance, but which did not roar with the white fury everyone associates with the word. And yet, and this is the part that matters, it is lava all the same. That cool black flow is not mud, though it looks like mud. It is not tar or motor oil, though it looks like both. It is genuine molten rock, magma risen from the deep heat below the rift, the same kind of journey that any lava takes, born of the same restlessness in the earth that builds every other volcano. It simply carries a different cargo. And to understand why that cargo cools and darkens where the ordinary cargo blazes, we have to go down, gently, into the chemistry of the two, and to do that we only really need to understand one element and one habit it has. That element is silicon, and the habit is its love of joining. Almost every volcano on Earth, very nearly all of them, erupts a magma built on silicate minerals. And the heart of a silicate is a tiny shape, a single silicon atom cradled by 4 oxygen atoms around it, a little pyramid that geologists call a silica tetrahedron. On its own, it is nothing remarkable. But these little pyramids have a powerful urge to link to one another, corner to corner, oxygen shared between them, building chains and rings and sheets and great tangled three-dimensional nets that run on through the melt. This linking, this joining of the tetrahedra into long networks has a name. It is called polymerization, and it is, in a sense, the secret architecture of ordinary lava. Picture what a network like that does to a liquid. The more the little pyramids link arms, the more the whole melt becomes a tangle, a thicket, a crowd of molecules holding on to one another and refusing to slide easily past their neighbors. The liquid grows thick and resistant and stiff. That resistance, that unwillingness to flow, is viscosity. And silicate magmas with all their linked networks can be enormously viscous, some of them so sticky they barely creep, so sticky they trap gas inside themselves until the pressure tears the mountain open. And all of that linking, all of that holding on, takes a great deal of energy to keep loose enough to move at all. To break those bonds, to keep the tangle fluid rather than frozen, the magma must be very hot. The heat is the price of the architecture. The 1100 degrees, the 1200, is the temperature the silica networks demand simply in order to stay liquid and to flow. And it is that same fierce heat, of course, that makes the lava glow, that fills it with the white and orange light we know, because anything that hot shines with its own fire in the dark and even in the day. So that is the ordinary story. Hot because it is sticky, sticky because it is linked, linked because of silicon's love of joining, and glowing because of the heat that joining requires. Hold that picture in your mind, the tangle and the heat and the light, because the lava of Ol Doinyo Lengai is the photograph turned inside out. For this lava has almost no silica in it at all. It is not built from those little pyramids and their eager linking. It is built instead from carbonate ions, the same family of compounds near enough as the soda in your kitchen cupboard, washing soda, baking soda, sodium carbonate and potassium carbonate gathered together into a melt. And the carbonate ion does not have silicon's habit. It does not reach out and link itself into endless networks. It does not build the tangled three-dimensional nets that stiffen a silicate melt. There is, in a carbonate liquid, almost no polymerization at all. The molecules sit loose, unjoined, free to slide past one another with hardly any resistance. And everything follows from that one absence. With no networks to hold the melt rigid, with nothing to keep the molecules clinging to their neighbors, the lava does not need to be kept ferociously hot just to stay liquid. It can be cool and still flow, cool and still pour, cool in a way no silicate could ever be without simply freezing solid. The high temperature was always the cost of the silica architecture, and where there is no silica architecture, that cost is never paid. So the lava rises at 500, 600 degrees, warm but not white, hot enough to burn but not hot enough to blaze, and because it is not hot enough to blaze, it does not glow with the great light. In the daytime, it shows you nothing but darkness, a black flow moving across the crater floor as quietly as oil down a pane of glass, and at night it gives back only the faintest dull red, a sullen ember of a glow where any ordinary lava would be a furnace of gold. And because nothing in it is linking, nothing in it is tangling, the very same absence that keeps it cool also keeps it astonishingly, almost unnaturally, fluid. We will come to that fluidity properly, to the thin, ropey sheets it leaves and the strange little towers it builds, but feel it now in passing that this is a lava that runs not like the slow, creeping stone of the films, but like something far closer to water, far closer to thin oil, a liquid so loose it seems to forget it is rock at all. So there it is, pooled in the crater in the thin hours before dawn. Black, quiet, almost gentle-looking, moving with a patience that does not suggest fire. Not the molten orange curtain of cinematography. Not the blinding river of Kilauea coursing down a slope at speed. This is something closer to the way warm tar might behave on a summer road, or the way thick oil finds its level slowly across a tilted surface, and if you were watching it for the first time with no one to tell you what it was, you might look for some other explanation. A mud flow perhaps, leaked industrial waste from a plant that doesn't exist for 200 miles in any direction. Something that had no business being here, on this steep volcanic cone above the Rift Valley floor, dark and patient and pouring. And then the light changes. Dawns in this part of Tanzania come quickly, the sun hauling itself above the horizon with a directness that has no interest in gradual transitions. 1 hour, it is a darkness thick with stars and the faint, dull glow somewhere below you in the crater. The next hour, the sky has moved through purple and orange and is settling toward the flat gold of early morning. And in that light, something is happening to what was flowing in the dark. The black crust where the lava has slowed and begun to cool is changing. Not dramatically, not all at once, but the change is real, and it is the most quietly extraordinary thing this mountain does. Perhaps more remarkable, in its way, than the temperature itself. The lava is turning white. Not everywhere, not instantly. It begins at the edges of a flow in the places that cooled first and have had the most time exposed to the air. A pale grey appears, and then the grey lightens. And then where the surface was most deeply black, there is now something approaching the colour of old plaster or dried salt. Within a few hours, The transformation is underway in earnest. By the time the sun is properly up and the heat of the morning has settled over the crater, some of the older flows are already the color of dirty snow. Some patches look almost white. The Hornito towers, the black spires the lava built through the night, still show dark at their bases where warmth persists, but higher up, where the surface cools and the air finds them, the bleaching has already begun. And by the next morning, much of what was black the night before is grey-white. The crater floor at that point looks less like the interior of a volcano and more like something dusted with ash or frost, or the residue of a slow and drifting snowfall that came not from clouds but from the rock itself. The reason for this is the chemistry, and the chemistry here is everything. Sodium carbonate is what the geologists call hygroscopic. It is a word worth sitting with for a moment, because its meaning is exactly what it sounds like once you hear it broken apart. Hygro, from the Greek for wet or moist, and scopic, from the Greek for watching or seeking. Hygroscopic materials seek moisture. They draw it toward themselves. Sodium carbonate, sitting in a dry room, will absorb water from the air without any prompting, without any effort, as a simple consequence of its chemistry. It wants the water, it reaches for it. The air in a room holds a certain amount of invisible humidity, water vapor, that we move through without noticing, and sodium carbonate, given the chance, will take that humidity and hold it. It is why the mineral form of sodium carbonate, the thing sold in shops as washing soda, has to be stored sealed. Left out, it drinks the air and goes damp. Now imagine what happens when that same chemistry sits exposed in a volcanic crater, open to the sky, open to the humidity that drifts in from the Rift Valley floor far below, open to the morning mist, to the light rains that come through seasonally, to the simple fact of an atmosphere full of the moisture that sodium carbonate finds irresistible. The freshly erupted nitrocarbonatite, still black, still warm at its surface, is already beginning this conversation with the air. The sodium carbonate molecules in the cooled crust are reaching for the water vapor around them. They absorb it, they react with it, and in reacting with water and with the carbon dioxide that shares the same air, the minerals at the surface begin to alter. Nyerereite, the mineral named for Tanzania's first president, is not stable in the presence of water, not at the temperatures and conditions of an open crater. Neither is gregoryite, named for the geologist who first mapped this rift. These are minerals that exist in a delicate equilibrium, a chemical balance that the rest of the world, with its rains and its oceans and its perpetual humidity, has entirely broken down everywhere else on Earth. Here, at the surface of a fresh flow, that equilibrium is broken one exposure at a time, one molecule of absorbed moisture at a time, and as it breaks, the chemistry shifts, and the dark minerals give way to pale carbonates, to sodium bicarbonate, and related compounds that are light in color, gray, white, chalky, and together they build up on the surface of the cooling flow until the entire texture and color of the lava has transformed. There is something almost meditative about the pace of it. This is not an explosion or a violent chemical reaction. It is slow, patient. The mountain does not hurry its transformation any more than it hurried its eruption. The black becomes grey the way evening becomes night. Gradually, without a clean line you could point to, the colour draining out of the rock in hours or days rather than all at once. You could lie very still beside a fresh flow, which you would not want to do for reasons we will come to later, but imagine it for a moment and watch the colour leave. Watch the glossy dark surface take on a duller, paler quality as the morning air moves over it. Watch the edges go first, watched the frost-like whitening spread inward from the older, cooler margins of the flow toward the newer, warmer center. When the rains come, the transformation accelerates. Nitrocarbonatite is extraordinarily soluble in water, far more so than ordinary basalt, far more so than almost any volcanic rock you might encounter anywhere on the planet. Rain landing on a fresh flow does not bounce off an impervious surface the way rain bounces off granite or cooled basalt. It soaks in, it reacts. It dissolves the sodium and potassium carbonates with an eagerness that would astonish you if you watched it, streaking the pale surfaces with channels where the minerals have washed away, carrying the dissolved compounds downslope in thin, caustic solutions. A white crust that took hours to form can be partially washed away in a single, heavy rain, the chemistry reversing and replaying in endless cycles across the crater floor as the seasons turn and the rains come and go. This is why there is almost no nitrocarbonatite anywhere else on Earth. Not because the volcanoes that produced it were rare. They may have been more common once, in deep geological time, when conditions in the mantle and in the crust favored this kind of magma more broadly. But because the rock itself is so unstable, so willing to be dissolved, so eager to react with water and air and turn into something else entirely, that even where it erupted millions of years ago, essentially nothing recognizable survives. Other carbonatite volcanoes exist, preserved in the geological record, but they are calcium-rich, a more stable variety, the kind that holds itself together against weathering. The sodium variety, the nitrocarbonatite, has simply not survived as itself. It has been altered, dissolved, washed away, transformed by the same hygroscopic chemistry that bleaches the lava white on the morning after eruption, but played out over millions of years instead of hours, until nothing remains that would tell you what it once was. Ol Doinyo Lengai is therefore a window into something that would otherwise exist only in inference and calculation. We know that carbonatite magmas have been produced at various places and various times in the history of the Earth because we can see the altered remains, the calcium-rich descendants, the geological fossils of what was once a similar process. But to see nitrocarbonatite erupting now, today, flowing down a crater, while a researcher with a temperature probe watches in real time, is to see something that should, by the logic of geological preservation, not be visible at all. It is a ghost that has not yet finished haunting, a magma type that has erased itself from the record everywhere else, and then, inexplicably, chose this one steep cone in northern Tanzania to go on existing. There is a particular quality to the way this lava moves that deserves its own attention, its own slow contemplation, because it is so unlike what you might expect from a volcanic flow that it takes a moment to fully register as real. The viscosity of nitrocarbonatite is extraordinarily low. Viscosity, if you want to hold it gently in your mind without the technical machinery, is simply a measure of a liquid's resistance to flowing. Honey has high viscosity. It clings to itself, it pours slowly, it remembers the spoon that stirred it. Water has low viscosity. As it runs freely, it finds every crack. It has no interest in holding its shape. Ordinary basaltic lava is somewhere in between, depending on temperature and composition, but it is certainly no honey. At 1,100 degrees it flows with some freedom, though it is still recognizably rock-like in its heaviness and its pace. Rhyolite, the sticky silica-rich lava of some of the world's most explosive volcanoes, is more like cold toffee. It barely moves, and when it cannot move, the pressure builds, and the explosion comes. Nitrocarbonatite is closer to water than to any of these. Not pure water, not quite, but something in the neighborhood of very light oil or thin syrup, a liquid that has almost no interest in resisting its own motion. When it pours from a hornito vent or spills from the edge of a lava pond in the crater, It does not creep. It runs. It spreads thinly across the crater floor with a speed and ease that seem wrong for something produced by a volcano, something that came up from the interior of the Earth. Researchers who have observed it describe flows that move quickly despite the low temperature, thin sheets spreading laterally in ways that basalt simply could not manage without being far hotter. The absence of viscosity, like the absence of silica networks, changes everything about how this lava behaves in the world above ground. And because it is so fluid, it makes things that normal lava cannot make with the same delicacy. It forms thin, ropey sheets, sometimes called pahoho-like, for their resemblance to the pahoho flows of basaltic volcanoes, but finer, thinner, with a texture that is almost papery when it cools. It forms tiny channels and rivulets. It pools in low points of the crater floor and then spills from those pools in thin, silver-black cascades when the pressure tips. The surface of a fresh flow caught in the right light has a quality almost like glazed ceramic, smooth, dark, with a sheen that looks more liquid than stone. And then there are the hornitos. The word itself comes from the Spanish, a diminutive of horno meaning oven, little ovens, small furnaces. The name gives you something of the shape, a cylinder, hollow, tapering slightly. But it does not quite prepare you for what these structures actually look like when you encounter them in the crater of Ol Doinyo Lengai. They rise from the crater floor as black spires, sometimes a meter tall, sometimes several meters, built from spattering lava that piled up around a vent and slowly constructed a chimney around the vent's opening. Lava pushes up through the hollow interior of the hornito and spills from the top, or spurts from cracks in the sides, or drools down the outer surface in thin black streams that cool quickly in the air and add another layer to the tower's walls. They are being built even as they stand. They are simultaneously architecture and process, structure and event. And they are fragile, more fragile than they look, because the very chemistry that makes nitrocarbonatite so fluid makes it unstable as a solid. A hornito will grow over hours or days, adding layers, gaining height, and then, when the pressure shifts, when the flow beneath changes direction, when the structure becomes too tall for its own thin walls to support, it collapses. Not with a great explosion or a thunder of rock necessarily, but with a slow leaning and a crumbling, the hollow tower falling in on itself and leaving a pile of dark rubble that another hornito may begin to build on almost immediately. The crater is a place of constant, quiet reconstruction. What was standing yesterday may be rubble today. What is rubble today may be the foundation of something new by next week. Expeditions that have visited the mountain on multiple occasions, returning months or years apart, consistently describe a crater floor that they do not recognize. Not because it has grown or shrunk significantly, the mountain itself is still the same steep cone, but because the micro-landscape within it has been completely remodeled. The hornitos that were tallest on one visit are gone. New ones stand where there was only flat crust before. Channels that carried lava in one direction now run another way because a collapsed hornito blocked the old channel and opened a new one. The crater is a city that is being perpetually demolished and rebuilt by the only contractor available, which is the lava itself, working with no plan except the one that pressure and gravity and chemistry impose together, to sit, again, just in imagination because the crater is genuinely dangerous, on the rim and watch this over hours would be to watch time operate at an unusual speed. Most landscapes change slowly enough that we cannot perceive the change. A river cuts its canyon over millions of years. A glacier retreats over centuries. A shoreline shifts over decades. But the crater of Ol Doinyo Lengai during an active, effusive phase is changing on the timescale of a single night's observation, and if you had the patience and the safety equipment and the good fortune to be in the right place at the right moment, you could watch a hornito grow by a visible amount in the time it takes to drink a cup of tea. The geological process made perceptible. The deep, slow work of the earth here, running at a speed the human eye can follow. There is one more quality of this lava worth sitting with before we leave the question of what it is and move toward the question of where it comes from. It is made at its heart of the same family of chemicals as things you might have in your kitchen or your laundry cupboard. Sodium carbonate is a compound so common, so thoroughly woven into the fabric of ordinary domestic life that it has many names. Washing soda, soda ash, sal soda. It is used in glass making, in soap making, in water softening, in baking, where the closely related sodium bicarbonate, just one step away in the chemical family, becomes the baking soda that makes cakes rise. Potassium carbonate appears in some baking powders in the production of certain types of glass and soap, in processes so familiar they barely register as chemistry. These are not exotic compounds, they are not the rare minerals of deep geology, found only in inaccessible deposits. They are, in the most literal sense, kitchen chemistry, and yet here they are, erupting from the interior of the Earth in a volcano. Coming up from depth in a melt that reaches nearly 600 degrees at its source, flowing across a crater floor in thin black sheets, building hollow spires several meters tall, and then, in the morning air, reacting with humidity and returning to something very like what you would find in a laundry box on a supermarket shelf. The mundane and the volcanic meeting in the most improbable location, the chemistry of the everyday briefly recruited into something as far from everyday as it is possible to get. And yet it would burn you. This is the point at which the domestic analogy reaches its limit, and it is a limit worth being clear about. Washing soda in high concentration is caustic. It is alkaline enough to irritate skin, to damage eyes, to do real harm if not handled carefully. And nitrocarbonatite, fresh from the volcano, is not a dilute solution. It is a concentrated melt of these alkaline compounds in contact with the acids and moisture of the human body, capable of chemical burns quite separate from the ordinary thermal burns you might expect from any hot substance. Climbers and researchers who have visited the crater describe the irritation of the volcanic gases, the caustic quality of the ash and dust when it contacts skin or eyes. The 2007-2008 explosive eruption, which we will return to later, because the story of that eruption is its own kind of reminder that cold lava is not the same as harmless lava, produced ash that had this same chemistry, alkaline and reactive, drifting across the surrounding landscape. The lava is not touchable, it is not safe. Its coolness, relative to basalt, is not an invitation. The mountain that makes the coldest lava on Earth is still a volcano, still a place of genuine danger, still a structure that can turn in ways that make caution the only reasonable response. The gentleness of the flow in the quiet phases, with the thin black sheets, the patient hornitos, the nightly building and morning bleaching, is real, and it is extraordinary, and it is worthy of the quiet awe this kind of darkness and strangeness invites. But it is the gentleness of a thing that has another face, and we will come to that face in time. For now, the crater in the hours just before midnight, the lava still moving in its slow black streams, the hornitos catching the faint, dull orange glow and throwing it back at odd angles, the air carrying the faint alkaline edge of the volcanic gases, the stars above the Rift Valley pressing down through thin air at nearly 3,000 meters of altitude. For now, there is something almost impossible to look away from in this. The spectacle of something that breaks the rules so quietly. No roaring, no blinding light, no rivers of orange fire racing down slope to threaten a village. Just dark, slow, patient flow. And the knowledge that by morning it will be white. And that transformation of the whitening is worth sitting with for a while, because it is one of the strangest things a landscape can do overnight, and the chemistry behind it is almost domestic in its simplicity, which makes it stranger still. When nitrocarbonatite cools and solidifies, it is not stable the way basalt is stable. Basalt hardens into something like a permanent record. It may weather over geological time, over thousands of years of rain and wind and freezing and thawing, but on a human timescale it simply sits there, dark and solid and obdurate. The rocks on a Hawaiian beach that were poured from the earth 2 centuries ago look more or less the same today as they did the morning they stopped moving. They have a kind of permanence that we associate intuitively with the idea of rock itself. Nitrocarbonatite does not have this permanence. It begins to change almost immediately. The dominant minerals in Lengai's fresh lava, nyerereite and gregoryite, those 2 compounds found essentially nowhere else in the natural world, are built around sodium carbonate and potassium carbonate. And sodium carbonate, when it meets air, when it meets the thin but real humidity even in the dry season above the Rift Valley floor, does something that a chemist would find entirely unsurprising and that a volcanologist still finds quietly astonishing. It begins to drink. Hygroscopic is the technical word. It means the substance draws water molecules out of the surrounding air and binds them. Sodium carbonate, the same compound at the heart of washing soda, the white powder that has been used to clean things, to cut grease, to soften water since the ancient Egyptians were pulling it from dry lake beds, is intensely hygroscopic. Left in the open air, it absorbs moisture and begins to change its crystal structure, incorporating water molecules, expanding slightly, transforming from one hydration state to another. It does not need rain. It needs only the air. On the crater rim of Ol Doinyo Lengai, especially at night, when temperatures drop and relative humidity rises, the fresh black lava begins this process within hours. The glossy black surface, the surface that looked, while it was flowing, like dark oil on dark stone, starts to pale. A film forms, thin and chalky, the color of ash or of the salt that rims Lake Natron's edges down below. Pale grey at first. Then, as the hours accumulate and the moisture continues to work, something closer to white. Not the bright white of fresh snow. Something softer. The white of old salt. The white of a frost that has been on the ground since before dawn and is thinking about melting. By the time the sun rises and the light changes the color of everything, the lava that flowed through the night has been transformed. Where there were black streams and glossy black pools and black spatter cones catching only the faintest dull glow, there is now something that looks from any meaningful distance like the crater has been dusted. Like something powdery and pale has fallen from the sky and settled over the whole floor. Not ash, or not only ash. The lava itself has changed color. The volcanic field that looked in the darkness like the interior of something alive and dark and working looks in the morning like a field of dirty snow, or like ground that has been touched by an early frost that has not yet decided whether to stay. And if by chance actual rain has fallen, which happens, the East African Rift Valley has seasons, and even this dry and extreme corner of northern Tanzania is not immune to rain, then the whitening accelerates dramatically. Rain dissolves nitrocarbonatite. It does not simply wet it and run off the way rain runs off basalt. It begins to incorporate it. The The sodium carbonates are water-soluble in a way that silicate rock is simply not, and a hard rain on a fresh lava field at Lengai can streak the white crust, can dissolve sections of it away, can leave a surface that looks partially erased, smeared, melted back towards something undecided between solid and liquid. The crater after rain looks different from the crater in the dry air before rain. It is always changing. It is never quite the same landscape from one visit to the next. This is, geologically speaking, deeply unusual. Most volcanic landscapes are stable on human timescales. You can visit Kilauea or Etna, and the flows from years ago look essentially as they did when they cooled. Lengai's crater floor is in a state of permanent, slow renegotiation with the air and the rain. The lava is not finished becoming what it will become, and what it becomes over longer time, over years and decades, is not rock in the conventional sense at all. Natrocarbonatite exposed to prolonged weathering eventually weathers away almost entirely. The sodium and potassium carbonates dissolve. What remains, if anything remains, is an altered residue bearing little resemblance to the original material. This is why natrocarbonatite does not survive in the geological record. This is the core of why Lengai is so precious to science, why researchers have been returning to its summit with their equipment and their samples since J.B. Dawson first described the mineralogy in 1962, and the geology community looked at his findings with considerable skepticism. The rock this volcano makes is a rock that erases itself. Older carbonatite deposits found around the world, and there are many, buried in the crusts of continents on nearly every landmass, are calcium-rich, not sodium-rich. They are what carbonatite looks like after the sodium variety has long since dissolved and been carried away by water. They are the fossil of a chemistry that once existed in a form something like Lengai's, but that has left behind only its altered remains, its bones, rather than its body. Lengai is the body, the only living specimen. When geologists say that Ol Doinyo Lengai is the only active natrocarbonatite volcano on Earth, they mean something more specific and more interesting than simply that it is rare. They mean that everywhere else this chemistry has ever expressed itself, the evidence has been progressively dissolved, altered, and replaced by something else. The record of sodium carbonatite volcanism across geological time is written in absences and alterations, in deposits that used to be one thing and are now another. Only here, in this one crater in northern Tanzania, above the lake whose alkaline waters share something of the same chemical ancestry, can the original thing be seen in motion, not reconstructed, not inferred, actually moving. The hornitos are part of this motion. They grow from the crater floor in the way that nothing else in common volcanic experience quite prepares you for. A hornito, the word is Spanish for little oven, a name borrowed into volcanology because of its resemblance to a small clay cooking dome, forms when lava moving beneath a solidified surface crust finds a crack or a hole and spits upward through it. The spatter cools and hardens around the vent. More spatter builds on top of that. Slowly, over hours or days of intermittent activity, a chimney rises. Some hornitos at Lengai have reached several meters in height. They are hollow, or nearly hollow, built of their own spatter, and they are black. Genuinely black in a way that even fresh basaltic lava rarely is, because fresh natrocarbonatite has none of the incandescent orange that normal lava carries within it. At night, the hornitos are the things that catch the dim glow most dramatically. They are vertical. They protrude above the general level of the crater floor, and the faint, dull orange that emerges from their vents, the only visual evidence in darkness that the material moving inside them is hot at all, turns them into something that looks from above on the crater rim like an array of very small, very quiet torches. Not blazing, not dramatic, Quiet orange windows in black towers spread across a floor that is otherwise dark and slowly whitening. Then a hornito collapses. It happens because the structure is built of fragile spatter and the activity beneath it shifts. The tower falls. The vent that fed it may seal, or it may find a new path, and in a few hours or a few days a new hornito begins to rise from near the ruins of the old one, or from somewhere else entirely, on the crater floor. The micro-landscape is never fixed. The map of hornitos that a researcher draws on one visit to the summit is already partially obsolete by the time they descend. Expeditions that have returned at intervals of months or years have found the crater floor reorganized in ways that make it difficult to identify landmarks from previous visits. It is a place that does not hold still. And through all of this movement, the slow black flows, the rising spatter towers, the bleaching and the dissolving and the rebuilding, the chemistry at the heart of it remains the same strange thing. Sodium carbonate, potassium carbonate, the carbonate family, the compounds that clean, that soften water, that form the white crust on a kettle's heating element in a hard water town, that drift as ash across the flat surface of Lake Natron and build up along its shores in pale mineral formations. The lava of Ol Doinyo Lengai belongs to the same broad molecular family as washing soda and baking soda. Sodium carbonate, the workhorse of household chemistry, the compound so mild and ordinary that it is used in food preparation, in swimming pools, in glass making. And yet, it would burn your skin. Not with heat, or not only with heat, but with chemistry. Sodium carbonate in concentrated form, in the form it takes fresh from a volcanic vent, is caustic. Alkaline in the way that a strong base is alkaline. It reacts with moisture, and skin is wet always with sweat and the natural oils that keep it intact. And that reaction is a chemical one, not merely a thermal one. The dust from the whitening crust is an irritant to eyes and lungs. The lava itself touched would cause chemical burns as readily as thermal ones. This is not a lava you could walk up to and examine with your bare hand. This is not a cold lava that is therefore a safe lava. And so the question that has sat quietly beneath everything described so far, beneath the flowing black rivers and the whitening crust and the strange hollow spires growing in the dark, that question now asks to be answered. Or rather, it asks to be approached. Because the answer, if there is one that satisfies completely, lives deep underground, in a place no instrument has ever directly reached, in a region of the Earth's interior where pressure and temperature conspire to do things that cannot be replicated in any laboratory with perfect fidelity. The question is this: where does nitrocarbonatite come from? Not in the geographical sense. We know where it comes from in that sense. It rises from beneath Ol Doinyo Lengai, from somewhere in the upper mantle or the lower crust beneath the Gregory Rift, pushed upward through the volcanic plumbing of a mountain that has been building itself from this strange material for thousands of years. That much is not in dispute. The question is a chemical one, a structural one, a question about what happens to rock and melt deep beneath the surface of the Earth in conditions that human beings have never directly observed and can only infer from what rises to the surface and from the physics of materials under extreme pressure. The leading model, and it is important to say that clearly, to hold it at arm's length with that word, model, the way careful scientists do when they are describing something inferred rather than witnessed. The leading model is called liquid immiscibility. Immiscibility is a word that sounds technical but describes something entirely familiar. Oil and water are immiscible. Put them together in a glass, shake the glass, watch what happens. For a moment, they mix, they blur into each other, they seem to become one cloudy liquid, and then given time they separate. The oil rises, the water falls. Two liquids that cannot remain combined, that have a fundamental molecular incompatibility, drift apart the moment the energy holding them together is removed. This is immiscibility, the inability to mix. The tendency to separate into two distinct phases when given the chance. The model proposed for Lengai's natrocarbonatite says something like this is happening far underground, but with molten rock instead of cooking oil and water. Deep beneath the Gregory Rift, the theory holds, there exists a silicate magma, a more conventional magma, of the family called nephelinite or melilitite, built on the silicon-oxygen framework that characterizes the vast majority of the world's volcanic rocks. This silicate parent magma is itself unusual. Nephelinite is not common, and its presence here is connected to the particular chemistry of the rift environment, where the thinning of the continental crust allows unusual mantle material to well upward. But unusual as nephelinite is, it is at least recognizably a silicate magma. It belongs to the same broad family as basalt and granite and rhyolite, even if it is a distant and exotic relative of those more familiar rocks. Within this silicate parent magma, the model proposes a separate liquid begins to form, a carbonate-rich liquid, a melt enriched in sodium and potassium carbonates, which has different properties from the surrounding silicate melt, which is incompatible with it at the molecular level in the way that oil is incompatible with water. And given time, given the right conditions of temperature and pressure as the magma body cools and evolves and moves upward through the crust, this carbonate-rich liquid separates out, it unmixes, it drifts apart from the silicate material the way oil drifts to the surface of a glass of water. And, being less dense, being more fluid, being a different kind of liquid entirely, it rises. It finds pathways through the rock. It makes its way upward through the conduit system of the volcano until eventually it reaches the surface and emerges from the vents in the crater of Ol Doinyo Lengai as natrocarbonatite lava. This model is elegant. It is consistent with the chemistry of what comes out of the volcano. The nephelinite and related silicate lavas that have erupted from Lengai in its explosive phases are plausibly the silicate counterpart to the natrocarbonatite, the other half of the unmixed pair. The two magma types fit together in this scheme as two products of a single parent, separated by the same process of immiscibility that separates oil from water, but operating at temperatures and pressures and timescales that dwarf anything in ordinary experience. But it is not the only model. There are researchers who argue that the natrocarbonatite originates differently, that it may not require a silicate parent at all, that the carbonate liquid could derive more directly from carbonate-bearing material in the mantle itself, without the intermediate step of unmixing from a silicate melt. The debate is genuine and ongoing. The Earth does not open up and explain itself. The conduits that feed Ol Doinyo Lengai are not accessible to direct observation. What the scientists have is what comes out at the surface, and what can be inferred from experiments conducted at high pressure in laboratory apparatus that approximate, but never perfectly replicate, the conditions kilometers below the ground. This is worth sitting with for a moment. The most important question about the most unusual volcano on Earth, how its magma forms, is still, in the fullest and most honest sense of the phrase, not entirely resolved. The leading model is compelling and has significant support, but the exact mechanism remains an area of active research and genuine scientific conversation. Ol Doinyo Lengai is a living laboratory, and the experiment it is running underground has not yet yielded a conclusion that all its observers agree upon. What does not require a model, what is simply observed fact, is what comes out at the surface. And what comes out at the surface has given scientists two minerals that exist in their pure natrocarbonatite form, essentially nowhere else on Earth. Two minerals that carry the names of men whose lives, in very different ways, became entangled with this strange corner of the world. The first is nyerereite. Nyerereite is named for Julius Nyerere, the first president of Tanzania, the man who led the country from its independence in 1961 and governed it for more than 2 decades, a figure who became one of the most significant political voices in the history of post-colonial Africa. Nyerere is remembered for many things: for his philosophy of ujamaa, a form of African socialism rooted in communal values and traditional ways of living together, for his efforts toward Pan-African unity, for the way he chose to leave power voluntarily, which was rare enough in the politics of the continent in that era to be remarkable. He is remembered as a teacher because he was one before he was a president, and something of the teacher's manner never left him. He is remembered as a man who read widely and thought carefully and cared genuinely and demonstrably about the dignity of ordinary people. That his name is carried by a mineral found in the lava of his country's most extraordinary volcano is a connection that is easy to pass over and worth pausing on. A mineral named for a president. A mineral found in the lava of a mountain that the Maasai, who have lived near it for centuries, call the Mountain of God. The naming of minerals is a small act, an act of scientific record-keeping, but in this case it places the name of a man who governed a human community alongside the chemistry of the deep earth, alongside the sodium and potassium carbonate structures that form in molten rock and emerge cooling and black from the crater of Lengai. Nyerereite, the mineral, does not know this. It is a crystal structure, a particular arrangement of atoms, but the name carries a history, and the history is not a small one. The second mineral is gregoryite. Gregoryite is named for John Walter Gregory, the Scottish geologist who, in the 1890s, travelled through East Africa and first described and named the East African Rift, the vast system of fractures and valleys and volcanic features that runs from the Afar region in the north down through Ethiopia and Kenya and Tanzania and into Malawi and Mozambique, where the African continent is slowly, over millions of years, pulling itself apart. Gregory's account of this journey, published in 1896 under the title The Great Rift Valley, introduced the concept of a rift valley as a geological structure to a scientific audience that had not yet had language for what he was seeing. He saw the shape of the land and understood that it was not arbitrary, that the long valleys and the escarpments and the chain of lakes, including the lake that would eventually be called Lake Natron, were all expressions of a single geological process, a vast tectonic wound in the surface of the continent. Gregoryite, the mineral, carries this name into the lava of Lengai. It is, like nyerereite, a sodium and potassium carbonate structure found in fresh carbonatite and essentially nowhere else in its unaltered form. The mineral exists because the lava exists, and the lava exists because the rift that Gregory named is still active, still pulling the continent apart, still providing the conditions under which the strange and unprecedented chemistry of Ol Doinyo Lengai is possible. Both minerals, nyerereite and gregoryite, are extraordinarily unstable by the standards of rocks and minerals. Most minerals persist. Quartz, the silica mineral that forms the backbone of granite and countless other rocks, persists across billions of years. It survives erosion and burial and pressure, and even, to some extent, the chemistry of the atmosphere. It is one of the most stable common substances on Earth's surface. Nyerereite and gregoryite are not like this. They are soluble in water. They react with humidity. They are the same compounds that vanish from the crater floor of Lengai within hours to days, dissolving into the ghostly white crust and then dissolving further into whatever water touches them. As minerals, they have essentially no durability. They exist in the geological record not as themselves but as the altered, calcium-enriched versions that replace them after water and time have done their work. This is the fact that makes Lengai so irreplaceable in a scientific sense, not just the fact that it erupts carbonatite, because carbonatite deposits are found in dozens of places around the world, old intrusions and ancient volcanic structures where carbonate-rich magmas have solidified and been preserved. But those preserved carbonatites have been altered. The sodium and potassium that characterize nitrocarbonatite have been leached away, replaced by calcium, transformed by groundwater and rainwater, and the slow work of chemical weathering over thousands or millions of years. What remains is a calcium-rich carbonatite, calcite, or dolomite-bearing, a rock type that geologists recognize and study, but that is a different animal from the original material. The original sodium and potassium carbonatite, the nitrocarbonatite, is gone, dissolved into the groundwater of geological time, leaving only its altered descendant as evidence that it was ever there. Lengai is the place where the original material can be seen, where the nitrocarbonatite that would elsewhere be known only from its altered remains is here, now, flowing out of the ground in real time, crystallizing nyerereite and gregoryite in the open air, offering itself to direct observation and analysis before the water and the weather have had their way with it. Every time a scientist climbs into the crater of Ol Doinyo Lengai and collects a fresh sample of nitrocarbonatite, and they do this carefully, with protective equipment and awareness of the volcano's unpredictability, they are collecting a substance that would otherwise exist only as a fossil of itself, known only from what it leaves behind when it dissolves. They are collecting the ghost before it has fully become a ghost. The man who first described this material in the language of modern geology was J.B. Dawson. John Barry Dawson, a British geologist who published his foundational description of the nitrocarbonatite lavas of Ol Doinyo Lengai in 1962. Before Dawson's work, the reports that reached the geological community from East Africa, reports of dark, cool, fluid lava in the crater of Lengai, were not entirely believed. Not because the observers were unreliable, but because what they described did not fit the framework. Lava at half the expected temperature. Lava that looked black and fluid like oil rather than incandescent like the inside of a furnace. Lava that turned white by morning. These were not the properties that the science of volcanology, as it stood in the mid-20th century, predicted or allowed for. The framework said lava is silicate, lava is hot, lava glows, lava is rock. What was being described from Lengai's crater was none of those things in the usual senses. Dawson's 1962 paper provided the chemical analysis, the measurements, the confirmation that what was coming out of Lengai was not a contaminated or weathered version of something normal, not a misidentification, not an error in the field observations. The instruments said what they said. The temperature of the lava was around 500 degrees Celsius. The composition was dominated by sodium and potassium carbonates. This was not silicate magma with an anomaly. This was a fundamentally different kind of magma. Dawson named it nitrocarbonatite, the natron-bearing carbonatite, the sodium carbonatite, and in doing so gave the geological community its first clear account of a lava type that had never been described from an active volcano before. One can try to imagine what it felt like to measure lava at that temperature for the first time. Not with wonder at the spectacle. Scientists in the field are busy, practical, focused on equipment and safety, and the logistics of working in a remote and difficult environment, but with the particular feeling that comes when an instrument reading contradicts everything the framework predicts. When the thermometer says 500 and the training says it should say 1100, the instinct is to doubt the instrument, to check the calibration, to take the reading again, and when the reading says 500 again and again, there is a moment of reckoning with the possibility that the framework is wrong rather than the instrument. that the mountain is doing something the science has not yet accounted for, that there is more to understand here than was previously suspected. The field measurements by Dawson and by subsequent researchers, H. Pinkerton, and others who have carried instruments into the crater across the decades since 1962, have confirmed and refined the temperature range. The lava emerges at roughly 500 to 600 degrees Celsius. The exact figures from different measurements cluster between about 510 and 590 degrees. The spread reflects real variation from vent to vent and from one eruptive phase to another, but the central fact is consistent. This is lava at approximately half the temperature of ordinary basalt. The coldest erupting lava ever directly measured on Earth, not as an estimate or an extrapolation, but as a field measurement taken at the vent itself. The physical setting in which this unprecedented chemistry occurs is itself a place of large and slow drama. The Gregory Rift, named again for that Scottish geologist who first mapped and named the broader system, is the eastern branch of the East African Rift, which is one of the few places on Earth where continental rifting is actively and visibly underway. Most of the ocean floors were once continental crust, and the process by which they separated, the rifting, the thinning, the intrusion of new material from below, the eventual flooding with seawater as the rift widened and deepened, happened over millions and tens of millions of years. And the evidence of it is now at the bottom of the Atlantic and the Pacific, submerged and largely inaccessible to direct observation. The East African Rift is one of the places where that process is happening now, or, to be more accurate about the timescale, happening at geological pace, which means at a rate that is real and measurable, but utterly imperceptible in a human lifetime. The African plate is not a single rigid piece of rock. It is pulling apart. Along the East African Rift, and specifically along the Gregory Rift in which Lengai stands, the crust is being stretched and thinned. The stretching creates the characteristic landscape of rift valleys, long, linear troughs bounded by escarpments occupied by chains of lakes. Lake Natron lies in this trough. So do Lake Manyara, Lake Ayasi, and others further along the system. The lakes are where they are because the ground between two elevated shoulders has dropped and the water has collected in the depression. The volcanic activity, including Lengai, but also other volcanic centers in the region, is a consequence of the thinning crust allowing material from the mantle below to rise toward the surface. Where the crust is thick, the mantle stays down. Where the crust is thin and still thinning, the mantle finds paths upward. And in the particular chemistry of this particular rift, with its unusual mantle material and its long history of carbonate-rich volcanism, those upward paths sometimes carry the ingredients for nitrocarbonatite. The shape of Ol Doinyo Lengai itself reflects a history that is longer and more varied than the nitrocarbonatite alone. It is a stratovolcano, a cone. The classic, almost archetypal volcanic shape. The shape a child draws when asked to draw a volcano, steep-sided and pointed, rising cleanly from the surrounding landscape. This shape is built by the accumulation of many eruptions over many thousands of years, layers of ash and lava and fragmental material stacked on top of each other, building the cone higher with each eruptive episode. Fuji is a stratovolcano. Vesuvius is a stratovolcano. The classic, dangerous, compositionally complex volcanoes tend toward this form. It is unusual for a carbonatite volcano. Most carbonatite occurrences, where they are found preserved in the geological record, are in the form of intrusive bodies, masses of crystalline rock that solidified underground, later exhumed by erosion, or in relatively low-profile volcanic structures without the dramatic steep cone that Lengai displays. The steep cone of Lengai reflects a volcanic history that includes the explosive phases, the ash-producing eruptions that built the cone's flanks with fragmental material alongside the quieter lava flows. The natrocarbonatite eruptions of the effusive phases are not what built the mountain to its nearly 3,000 meters of elevation. Those gentle, dark flows are the most recent, most visible expression of Lengai's activity, but the mountain itself is the product of a longer and more violent history. Nearly 3,000 meters, 2,960 meters above sea level, which is approximately 9,700 feet by the other common measure. It rises from the floor of the Rift Valley, which is itself elevated above sea level, and so it commands a view over a landscape that is already high and dry and ancient feeling. The Rift Valley floor, with its lakes and its sparse acacia scrub, and its distant escarpments shimmering in the heat. From a distance, on a clear day, Lengai's cone is visible as a clean and formal shape against the sky, dark grey against blue or white against white cloud, a mountain that looks like what a mountain is supposed to look like and gives no outward indication, from that distance, of the extraordinary chemistry taking place in the crater at its summit. And this is perhaps the most quietly remarkable thing about Ol Doinyo Lengai when seen from a distance. It looks like a mountain. It looks like an ordinary, if steep and isolated, volcanic cone. The strangeness is hidden inside it. The anomaly is in the chemistry, which is invisible at the scale of the whole mountain. What is happening in the crater, the black flows, the strange spires, the crust that whitens toward morning, is contained within the summit, within the walls of the cone, invisible to anyone looking at the mountain from the valley floor or from the shore of Lake Natron to the north. The mountain keeps its secret well. It is only when you are inside it, at the rim looking down, that the strangeness becomes visible. Only when you are close enough to feel the heat, such as it is, half the heat of ordinary lava, but still more than enough, and to see the flows moving. The closeness required to perceive what makes Lengai unusual mirrors something about the geological work done to understand it. The secrets of this mountain are not available from a distance. They required someone to go there, to descend into the crater, to collect samples, to apply the analytical instruments to the material itself. J.B. Dawson went there. He did the fieldwork that produced the 1962 paper that changed the understanding of what volcanic lava could be, and he did this in a place that is genuinely remote, in northern Tanzania, in a rift valley, at a summit that requires a serious climb, and in an environment where the volcano itself is unpredictable, and the lava, though cooler than any other on Earth, is still dangerous in ways that require caution and preparation. The remoteness of Lengai is not incidental to its story. It is part of why the mountain was not scientifically described until the 20th century, even though the Maasai have known it and lived near it for far longer. The mountain exists in a part of the world that European geological science reached late. The rift itself was only named and systematically described in the 1890s when Gregory made his journey. Lengai, as a subject of formal volcanological investigation, is in many ways a young field of study, not because the mountain is young, it is not, but because the scientific attention arrived recently, and the work of understanding it is still ongoing, still producing new papers, still refining the models. The rift in which it stands is tearing apart the African continent at a rate of a few millimeters per year, slow by any human measure, but inexorable. Given enough time, and the Earth has time in quantities that dwarf anything in human experience, the Gregory Rift and the broader East African Rift system will open wider, the crust will thin further, the sea will eventually find its way into the depression, and what is now an inland system of lakes will become a new ocean floor. This is the prediction that the physics of rifting makes, and the geological record of how the Atlantic formed supports it. The process takes tens of millions of years, but it has started. The ground beneath Lengai and Lake Natron is moving, the continent is slowly dividing, and the volcano stands at the edge of that division, its unusual chemistry a product of the unusual mantle material that rises through the thinning crust, a few millimeters per year, the width of a finger perhaps over the course of a year. And yet accumulated across millions of years, this becomes the Atlantic Ocean. This becomes the gap between continents, the same process that separated Africa from South America, that opened the floor of the sea between them, is underway here in northern Tanzania, in its early and as yet small-scale stages. Lengai is not just a strange volcano, it is a strange volcano situated at one of the places where the future geography of the planet is, very slowly, being written. The thinning crust allows the mantle to contribute its material to the volcanic system, and the mantle here, in the East African Rift, is not generic. It has its own character, its own particular chemical signature, the result of billions of years of geological history and of the specific circumstances of rifting in this region. The carbonate-bearing material in the mantle, the carbon that will eventually, through the processes of melting and unmixing and ascent, express itself as the sodium and potassium carbonatite of Lengai's lava. That carbon has been there, cycling through the deep earth for an unimaginably long time. The carbon in nyerereite and gregoryite and in the nitrocarbonatite lava that flows across the crater floor was once, perhaps, in the atmosphere, or in the bodies of ancient organisms, or in the seafloor sediments of oceans that no longer exist, subducted into the mantle over millions of years and held there, transformed there, until the rifting of this rift opened a path for it to rise again. Carbon cycles through the Earth on time scales of millions and hundreds of millions of years. The carbon in the atmosphere today, in the oceans, in the rocks, is the same carbon that has always been here, moving between reservoirs, atmosphere, ocean, crust, mantle, in great slow circuits that dwarf the carbon cycle we discuss in the context of climate and combustion. Lengai's nitrocarbonatite is a small but real part of that deep cycle. The carbon that emerges from the crater as carbonate lava is carbon that has been in the mantle long enough for its origin to be effectively unknowable. It is returning to the surface in a form so unfamiliar that the first scientists to measure it did not immediately believe their instruments, and yet it is the same element, the same carbon, cycling through. This is perhaps one of the reasons why Lengai, looked at from a certain angle, feels like a place where the deep interior of the Earth is more visible than usual. Most volcanoes present the mantle's work in a form that has been heavily processed. Silicate magma, familiar in composition, familiar in temperature, familiar in behavior. Lengai presents something closer to the raw material. The carbonate chemistry, the low melting point, the fluid, quick-moving lava that carries so little silica that it behaves more like water than rock. It is as if the usual processing has been partially bypassed, and what arrives at the surface is something less transformed, less worked over by the long journey through the crust, less recognizable as lava, but in some ways more directly connected to the chemistry of the deep earth. And then the water takes it. The rain and the humidity of the Rift Valley air, the seasonal rains that cross this part of Tanzania and change the landscape from dry to briefly green and back again. The water dissolves the nitrocarbonatite almost immediately. Nyerereite dissolves. Gregoryite dissolves. The black crust whitens and crumbles and washes away. What was lava becomes soil of a kind, becomes the alkaline chemistry that feeds into Lake Natron to the north and contributes to the extraordinary and strange ecosystem of that lake. The carbon returns to the surface cycle, the sodium and potassium enter the groundwater and the surface water, and the mineral evidence of the eruption begins almost immediately to erase itself. In the craters of other volcanoes, lava from thousands of years ago is still there, still recognizable, still analyzable? In Lengai's crater, lava from last month may already be gone, dissolved into the floor, replaced by new flows, the surface constantly renewed and constantly destroyed. The geological record of this volcano is, in the most literal sense, being erased as it is written. The mountain produces and dissolves its own history in real time. To study it is to study a process in its moment, not a process in its preserved remains. Dawson understood this. The scientific community that received his 1962 paper understood it once they accepted the data. Every geologist and volcanologist who has climbed to Lengai's crater since has worked with an awareness that what they are seeing is not stable, that the sample in the hand will not look the same tomorrow, that the mineral they are examining will not survive long enough to become a conventional geological record. There is urgency to the work, not the urgency of danger exactly, though the danger is real, but the urgency of transience. The lava of Ol Doinyo Lengai is a message written in a soluble ink, and the rain is always coming. And yet, for all the urgency that drives the scientists who climb to its crater, with their instruments and their sample bags and their awareness of transience, the mountain itself has always meant something else entirely to the people who have lived beneath it. The Maasai have known Ol Doinyo Lengai for as long as their oral history reaches, which is to say, for a very long time. And what they have known it as is not an anomaly of carbonate chemistry or a living laboratory of low-temperature petrology. They have known it as the dwelling place of Engai. That name is sometimes written Enkai, sometimes Ngai, and the transliteration varies across the scholars and travelers and missionaries who have recorded it, but the meaning is settled and the belief is living. Engai is the god of the Maasai, and Ol Doinyo Lengai is the mountain where Engai is most present, most reachable, most likely to hear a prayer spoken into the wind at the crater's edge. The name of the mountain itself in the Ma language means mountain of God. Not a mountain sacred to a god, not a mountain where a god once appeared, but the mountain of God, as if the summit and the deity are not merely associated but continuous. The peak a part of the presence a part of the peak. In a landscape of extraordinary volcanic formations and alkaline lakes and the great sweep of the East African Rift, this particular cone has been set apart by the people who live in its shadow, and has been set apart for reasons that, if you spend long enough looking at the mountain, do not seem entirely mysterious. Consider what the Maasai have observed across generations of living near this place. They have seen the mountain smoke and steam and occasionally roar. They have seen it quiet for years and then erupt again. They have seen the lava flow dark from its crater, black as night. And they have seen that same black lava turn white as the day advances, as if the mountain were changing its mood or its face or its intention. And they have understood Engai as a god with, precisely, two faces. Engai Narok is the black god, the benevolent one, the god who brings rain to the savannah, who sends the grass up green after the dry season, who is gentle and generous and life-giving. And Engai Nanyokye is the red god, the one associated with lightning and drought and punishment, the aspect of the deity that is fearful rather than comforting. Black and red, gentle and wrathful. The same god, two expressions, two moods, two possibilities, held in the same divine presence over the same sacred mountain. You could say the Maasai arrived at this theology through observation, and you would not be wrong. The mountain is black when it is in its gentle phase, pouring cool, dark lava quietly through the Hornitos, building and rebuilding its miniature crater landscape with a kind of patient industry that is not alarming to watch from a distance. And the mountain is, in its violent phase, dramatically red and orange, hurling ash, an incandescent ejector skyward, making a sound that carries across the rift floor, turning the sky above the Gregory Rift grey with particulate, black Lengai and red Lengai. The volcano's own two moods, given a divine name, given a theological framework, given a face. The first geologists who came to Lengai were there to measure and sample. The Maasai who had preceded them by centuries were there to pray. It would be easy and wrong to arrange these two relationships in a hierarchy, to say that one understanding supersedes the other, or that the scientific account replaces the sacred one. What is more honest and more interesting is to notice that the Maasai read the mountain's dual nature with considerable accuracy, not because they had thermocouples or mass spectrometers, but because they lived with the mountain across time and watched it long enough to see that it had two modes, two registers, two ways of being, and they built their theology around that observation. When J.B. Dawson climbed to the crater in the years before his 1962 paper and found lava that measured around 510 degrees Celsius, where he had expected something above 1/100, he was discovering, with instruments what the Maasai had already named with language. The pilgrimages to Ol Doinyo Lengai are not folklore. They continue. Maasai men and women have made the climb to the crater's edge to pray, to leave offerings, to speak to Lengai directly in the place where the mountain and the deity are understood to be the same thing. The climb is not easy, the mountain is steep and the terrain is demanding, and the crater, when it is active, is genuinely dangerous. But the difficulty is part of the meaning. You do not arrive at the dwelling of a god without effort. The mountain asks something of the pilgrim, and the pilgrim gives it, and arrives at the summit changed by the going up, by the physical fact of having ascended towards something understood to be sacred. There is something worth pausing on in this era when volcanologists arrive with GPS units and gas sensors and protective gear rated for caustic environments. The mountain is still the same mountain. The crater is still the same crater. The lava that flows from the hornitos at the bottom is still carbonatite, still 500 degrees, still turning white before afternoon. And the people who have lived longest with this mountain have always understood that it holds something that exceeds measurement. The scientists would not phrase it that way, and they are not wrong to measure rather than to pray. But the Maasai are not wrong either. The mountain is genuinely strange. It genuinely exceeds ordinary expectation. It is, in the most literal scientific sense, unlike anything else on Earth. If you were going to designate a mountain as the dwelling of a god, this would be a reasonable choice. To the north of Ol Doinyo Lengai, close enough that the two form a single landscape in the mind, lies Lake Natron. The lake takes its name from natron, the sodium carbonate mineral, and the name is descriptive in the most direct possible way. Lake Natron is one of the most alkaline bodies of water on Earth. Its pH approaches that of ammonia. Its surface, in the dry season, turns a deep blood red, stained by the halophilic microorganisms, the salt-loving bacteria and algae that are among the very few forms of life able to survive in water of that chemistry. The red color is real, and from above, from a satellite image or an aircraft, the lake looks like something spilled from the mountain above it, a slow seeping of the volcano's most dramatic chemistry down into the basin of the rift. The connection between the lake and the mountain is not metaphorical. The same sodium carbonate chemistry that makes Lengai's lava extraordinary also contributes to the alkaline loading of the lake. The volcanic system underlying the area releases sodium and carbonate into the groundwater and surface drainage, and that chemistry concentrates in Natron's shallow, evaporating waters. The mountain feeds the lake, chemically speaking, in the same way that any watershed feeds its downstream water body, except that here the upstream source is a carbonate volcano and the downstream receiving basin is a hyperalkaline soda lake, And the result is one of the stranger ecosystems on the planet, the birds of Lake Natron. Lesser flamingos breed at Natron in numbers that can reach into the millions, making the lake one of the most important flamingo breeding sites on Earth. They are drawn precisely by the caustic water, which protects their nests on soda islands from most predators, and by the cyanobacteria that bloom in the alkaline shallows and form the basis of the flamingo's diet. The same chemistry that would chemically burn human skin or strip the color from clothing is the foundation of an entire flamingo civilization at the lake's edge. Life has found, as life tends to find, a way to use the inhospitable as a home. And then there are the photographs that Nick Brandt took at Lake Natron, images that circulated widely and generated a great deal of alarmed commentary about a lake that turned animals to stone. The images showed calcified birds, flamingos and other water birds, or their bodies encrusted in a pale mineral coating, preserved in postures of flight or rest, transformed into something uncanny and beautiful and strange. The photographs are real, the calcification is real. Animals that die at Lake Natron, particularly birds, can become coated in the sodium carbonate and bicarbonate minerals from the water as their bodies dry in the alkaline shallows, creating a calcite or mineral crust around the form of the creature that can preserve the shape long after the organic material would otherwise decay. What the popular framing of these images sometimes overstates is the speed and the mechanism. The lake does not petrify animals on contact. It does not kill the birds by calcification in the way that some dramatic retellings suggest. What it does is chemical and gradual and real. Dead animals at the shoreline or in the shallows over time and with repeated wetting and drying in the alkaline water accumulate a mineral incrustation. The result is genuinely remarkable and the photographs are genuinely arresting, but the process is slower and quieter than the phrase "turns animals to stone" implies. The chemistry is doing what sodium carbonate chemistry does, which is to leave a mineral deposit behind when water evaporates. And in this case, the substrate is a bird rather than a rock face, and the result is something that looks like sculpture. The same sodium carbonate that flows from Lengai's hornitos in dark, cool streams, that turns white within hours of reaching the crater air, that dissolves in rain and enters the groundwater and eventually the lake. That same compound is responsible for the calcified birds of Natron, for the blood-red water, for the millions of flamingos that breed in a place that nothing else will approach. The mountain and the lake are one system, one chemistry, one strange and interconnected expression of the sodium carbonate richness that makes this corner of the East African Rift unlike anywhere else on the planet. Standing at the lake's edge and looking south to the mountain is to see the system whole, or at least to feel the wholeness of it, even if the mechanisms require a laboratory to fully articulate. The mountain makes the lake feeds the birds. The birds draw the scientists and the photographers and the observers who come to document the strangeness and go home changed by it. And all of it begins with the nitrocarbonatite, with the magma that unmixed from its silicate parent miles below the surface, that rose through the cone of a stratovolcano in the Gregory Rift, that emerged at 510 degrees where 100 was expected, and that turned black in the daylight and white by morning. But the mountain's gentleness, its cool, dark flows, and its steady hornito building is not the whole of its character. The Maasai understood both faces of Lengai, and the geologists have learned, sometimes with alarm, that Lengai is capable of demonstrating the second face with very little warning. The 2007 and 2008 eruption was not a gentle effusion of dark carbonate lava. It was something different in register entirely, a reminder that beneath the calm chemistry of the nitrocarbonatite there is enormous geological energy, that the rift is an active and dynamic system, and that a volcano capable of producing cool black lava is also capable of producing ash columns and explosive detonations that alter the shape of the crater itself. In 2007, Lengai shifted modes. The crater, which had been building its familiar landscape of hornitos and dark ropey flows and white-crusted pools, began to produce something else: ash. Grey, alkaline, fine-grained volcanic ash, the kind produced not by effusive lava but by explosive fragmentation of magma under pressure. The ash column rose into the air over the rift. The eruption continued into 2008, and when volcanologists were able to assess the crater afterward, they found it dramatically changed, deepened by the violence of the explosive phase, the familiar micro-landscape of spires and flows replaced by a new morphology, the mountain having, in effect, redrawn its own interior. It was not the first time. The recorded history of Lengai's behavior, which extends back through the 20th century with varying levels of detail, includes earlier explosive episodes: 1917, 1940 and 1941, 1966 and 1967. These are the dates that appear in the documented record, though the mountain's habit of erasing its own geological evidence means that the deeper history of its explosive phases is not fully legible. The nitrocarbonatite does not preserve itself. What does survive in the layers of ash and in the altered country rock around the volcano's flanks suggests that the alternation between effusive and explosive behavior is a recurring feature of Lengai's long life, not an anomaly. After 2007 and 2008, the effusive activity, the gentle carbonate lava flows, the hornito building, the quiet pooling of dark liquid in the crater, gradually returned. The mountain came back to its black-faced mode, and scientists who had watched the explosive phase with concern returned to find the familiar strangeness reasserting itself. The cool lava flowing again, the crater rebuilding, the white crust forming each morning on the previous night's dark flows. The cycle continues. The mountain oscillates, Engai Narok and Engai Nanyokye taking turns. For the researchers who work on Lengai and for the climbers and guides and curious visitors who attempt the approach, the danger profile of the mountain is something that requires careful understanding, and easy framing gets wrong in both directions. The low temperature of the lava, 500 degrees where basaltic lava would be 100 or more, can, if framed carelessly, suggest that Lengai is a safer volcano than its counterparts, as if the reduction in temperature translates to a reduction in risk. This is not the case. The nitrocarbonatite lava is still lava. 500 degrees Celsius will do everything that anyone who has ever been near a fire understands fire to do, with the significant addition that the chemistry of sodium carbonate makes the lava and its derived dust and ash aggressively caustic. Nitrocarbonatite reacting with moisture, with sweat on skin, with the damp surface of the eye, with the mucous membranes of the throat and lungs, can cause chemical burns. The fine particulate that the mountain produces during active phases is an irritant to eyes and respiratory tissue. Researchers who work at the crater rim wear protective equipment not simply against heat but against chemistry, because the heat alone, while not at the extreme of basaltic conditions, would burn, and the chemistry adds a dimension that even ordinary volcanic caution does not automatically cover. And then there is the mountain's demonstrated capacity for sudden transition, for moving from effusive calm to explosive violence in a way that the 2007-2008 episode illustrated, and that the historical record of earlier eruptions confirms. Climbers have been caught by changes in the volcano's activity during ascent. The approach to the crater is not a casual excursion. The mountain is remote, the terrain is steep, the altitude at nearly 2,960 meters means that the climb itself is demanding before any volcanic consideration is added, and the chemical environment at the crater is hostile in ways that are not always immediately visible. The lava looks, as has been said many times, and will be said again because it is true and because it matters, more like mud than like fire. It does not glow dramatically. It does not make the most obvious of volcanic announcements, and that visual quietness can be misleading about what it actually is and what it actually can do. The honest account of Ol Doinyo Lengai is one that holds both of these things simultaneously. The genuine wonder, which is real and enormous and not diminished by the danger, and the genuine hazard, which is real and not diminished by the wonder. The mountain is extraordinary. It is also a mountain that has surprised geologists and injured climbers and reshaped its own crater with explosive force. Both of these are true, and the mountain is large enough to contain both. What Lengai represents when you step back from the chemistry and the Maasai theology and the calcified birds of Natron and the 2007 ash column and J.B. Dawson's measured temperatures and the dissolved minerals and the erasing record. What the mountain represents when you try to take it whole is something about the variety of the world that exceeds ordinary expectation. We build our models of how things work from accumulation. Lava is hot, lava glows, lava is rock or becomes rock, and the rock endures. These are not wrong observations. They describe the overwhelming majority of volcanic activity on Earth and have described it correctly for as long as volcanoes have been studied. The model is built from an enormous sample, and the model is essentially right. And then there is one mountain in northern Tanzania, steep and striking against the sky of the Gregory Rift, where the model fails quietly and without apology, where the lava is cool, where it flows dark, where it turns white by morning, where it dissolves rather than endures, where the minerals that compose it are named for a president and a rift geologist and are found essentially nowhere else on Earth in their natural erupted state, where a living faith names the mountain as the home of a god who has, like the mountain itself, two faces, one gentle and dark, one wrathful and red. Lengai does not announce its strangeness loudly. This is perhaps the deepest thing about it. It sits in its rift valley. It produces its cool, dark flows. It builds its horny toes and lets them fall and builds them again. It contributes its sodium chemistry to the lake to the north and through the lake to the flamingos that breed there and through the flamingos to the ecosystem that depends on them. It erases its own record day by day, flow by flow, the soluble lava becoming the alkaline soil, the message written in dissolving ink, the geological text that unwriting itself even as it is read. And on certain nights from the crater's edge, where the lava moves in thin dark sheets and glows with only a low reddish light, barely enough to see by, the mountain looks less like a geological feature and more like something that is simply, quietly, different from everything else. Not louder, not more dramatic, just different, just itself, the only one. There is something to rest in that. In the idea that the world still contains, in a known location on a mapped continent, in a well-studied rift system, a place that breaks the rules not through concealment but through existence. Lengai has not been hiding. It has been there, smoking gently, erupting its dark chemistry, turning white in the morning light, receiving the prayers of the Maasai who climb to its summit and the instruments of the scientists who follow them, and being simply the one thing it is. The only active carbonatite volcano on Earth, the only place where nitrocarbonatite lava flows under the open sky, the only mountain where the lava dissolves itself in real time, the only peak that deserves, by the evidence of its own chemistry, the name the Maasai gave it long before any geologist arrived with a thermocouple, Mountain of God. Not because the Maasai lacked other explanations, but because the mountain, when you sit with it long enough, seems to require a category that ordinary language reaches for and ordinary science has not quite finished mapping. The crater is quiet tonight. Or it is not quiet. Volcanoes are rarely fully quiet. and Lengai's inner life continues beneath whatever surface calm the night presents. But the image of it, held in the mind from this distance, is of a kind of stillness. The hornitos stand. Some will have collapsed since the last expedition photograph. Others will have grown. The lava that pooled in the floor of the crater today is already beginning in the night air to lose its moisture to the atmosphere, the sodium carbonate drawing the humidity toward itself, the surface beginning its slow shift from black toward the grey-white that will be complete by the time the sun comes over the rift wall in the morning. The water table moves through the alkaline rock in the dark beneath the mountain. The slow geological rhythms of the rift continue, the continent still separating along the line that J.B. Dawson's era of geologists first fully mapped, and that continues its patient widening at a rate measured in centimeters per year. Continent time, the kind of movement that is invisible in a human life and undeniable across a geological one. Lake Natron, to the north, is the color of blood in the last light, or would be if there were anyone there to see it. The flamingos have settled somewhere, or some of them have, the millions of smaller lives going on around the chemistry of the lake, undisturbed by the philosophical dimensions of the chemistry that sustains them. The sodium carbonate in the water is simply what the water is. The microorganisms in the shallows are simply alive. The flamingo chick in the nest on the soda island is simply warm. And above it all, visible from the lake's northern shore on a clear day, the cone of Ol Doinyo Lengai rises into the sky of the rift. Steep, dark. Smoking, probably, in the thin atmospheric way of active volcanic vents that are always releasing something. The Mountain of God, as it has always been called, as it will go on being called, as it deserves to be called. You have come a long way tonight, in the quiet way that sleep allows. You have travelled, without moving, to a country of black lava and white morning crust, to a crater floor of hollow spires and cool, dark flows, to a lake that runs red with life, that thrives in chemistry, that would burn skin, to a mountain that the geologists measure and the Maasai pray to, and that both, in their different ways, approach with something that resembles awe. If you are still here, you have heard what the mountain is. You have heard why its lava is black, where other lava burns orange, why it runs cool at 500 degrees where basalt demands more than twice that, why it turns white in the hours after it flows, why it dissolves rather than endures, why it is the only one left on Earth, why the Maasai named it the way they named it, why the naming was not wrong. You have, in the slow way that understanding arrives when the body is quiet, taken in the mountain's strangeness and held it and let it settle. If you feel moved to share where in the world you are listening from tonight, the doc is open. The comments are there and I read them. It is a genuine pleasure in the particular geography of late night to know where these stories find their listeners, which shore, which hemisphere, which city going quiet around you as you drift. Leave a word if you want to, or don't. The mountain will still be there in the morning, rebuilding its hornitos, turning its lava white, erasing and rewriting its own record in the cool Tanzanian air. You have done enough for one day. The chemistry can continue without you. The rift can widen its centimeter in the dark. The flamingos on Lake Natron do not need watching. Set down whatever remains of the evening. Let the black lava turn white in its own time. Let the mountain hold whatever it holds. Tie off here at the wisdom docks. The tide will wait till morning. There is one more thing the mountain holds, and it is perhaps the most quietly astonishing of all the things gathered here tonight. The name, Ol Doinyo Lengai. In the Ma language of the Maasai, the people who have lived beside this mountain and beneath its plumes for as long as the oral record reaches, those three words resolve into something very simple and very large: mountain of God. Not a mountain associated with a god, not a mountain where a god was once glimpsed, but the mountain that is, in itself and without reservation, the dwelling of Ngai. Ngai, written sometimes Enkai, sometimes Ngai, is not an easy deity to summarize in a few sentences, because the Maasai understanding of Ngai is not a simple thing. What can be said, and what has been recorded by ethnographers who have listened carefully, is that Ngai carries within the single name two distinct natures, two faces turned toward the world. There is the black Ngai, the gentle face, the face associated with rain and with the green grass that follows rain, with cattle growing fat in the wet season, with blessing and abundance. And there is the red Ngai, the wrathful face, the face of drought and punishment, and the kind of divine anger that a people dependent on rain and pasture would fear above nearly everything else. The Maasai, watching Ol Doinyo Lengai over generations, watching it pool its black lava gently in the crater, and then, without sufficient warning, crack open in a fury of ash and grey explosive force, named something true. A mountain with two faces, a god with two moods, the black of the gentle lava and the red of the eruptive rage. Whether this correspondence was recognized consciously or settled into the tradition the way all deep truths settle, slowly, through accumulated watching, it is there. The mountain is the deity, and the deity has the mountain's own nature. It is, depending on how you hold it, a remarkable coincidence or a very old and very careful piece of observation. The Maasai have made pilgrimages to this mountain, not archaeologists guessing at ancient behavior from scattered artifacts, but a living tradition of people walking toward the place where Ngai lives, approaching with the kind of attention and seriousness that a living faith, not a metaphor, demands. The mountain is not a symbol of something sacred. It is, within that understanding, the sacred thing itself. That is worth sitting with for a moment before we move on to the lake. To the north of the mountain, close enough that the same volcanic chemistry threads through both, lies Lake Natron. It is a hyper-alkaline body of water. Soda lake is the technical term, though the phrase hardly captures what the lake actually looks like. The waters of Natron run an extraordinary blood red in places, stained by the pigments of the halophilic microorganisms, salt-loving bacteria and algae that are among the very few living things that can survive in water, that alkaline water, whose pH approaches that of ammonia, water fed by springs carrying the same sodium carbonate chemistry that builds the white crust on Lengai's cooling lavas. The lake is not blue, it is not green. It is, in the right light and season, the color of something that looks like it should not exist. The lake has also given rise to a set of remarkable photographs, images by the wildlife photographer Nick Brandt, who documented the bodies of birds and bats preserved in the lake's caustic shallows. The calcification is real. Animals that die in Lake Natron can be coated in mineral deposits, preserved in poses of terrible stillness, the sodium carbonate working through them and leaving something that resembles stone. The photographs have been reproduced widely, and the popular framing that surrounds them sometimes suggests an almost instantaneous process, a creature landing on the water and turning to mineral in moments. That is an exaggeration. The calcification is genuine, and it is eerie, and it is enough. The chemistry does not need embellishment. The lake does not need to be more alarming than it already is. What it is, stripped of the overstatement, is a body of water so caustic that it can preserve the dead in mineral casts, fed by the same sodium chemistry that flows from the slopes of the mountain to the south, the mountain of God turning its dark lava white and sending its chemistry downhill to color a lake the shade of old blood. The mountain itself has not always been gentle. The long, effusive periods, the years and decades when nitrocarbonatite simply pools and spreads in the crater, building hornitos, resurfacing the crater floor in black that fades to white, the quiet chemical housekeeping of an unusual volcano. Those periods can give a false impression of stability. Lengai is not a stable mountain. It is a mountain that alternates between its two faces just as Lengai does, and the periods of gentleness do not guarantee the gentleness will continue. There were explosive episodes in 1917. There were further eruptions in 1940 and 1941, documented and serious. In 1966 and 1967, the mountain erupted again with enough force to alter the crater, but the eruption that most clearly demonstrated what the mountain is capable of when it turns its red face to the world was the one that began in 2007 and continued into 2008. That eruption was not a gentle pooling of carbonatite lava. It was an explosive phase that blasted grey ash high into the Tanzanian air and deepened the crater dramatically, rearranging the interior of the mountain that scientists had spent decades carefully mapping and photographing. The hornitos, the delicate black spires, the thin, ropey sheets of cooled lava, all of it remade. The 2007-2008 eruption was a reminder, emphatically stated in ash and force, that the cold mountain is still a mountain, that the low temperature of the lava does not mean low energy in the system overall, that something very old and very pressurized lives beneath the crater floor, and that it has its own schedule. This is the honest caveat the mountain requires. Cold does not mean safe. The lava that flows at 500 degrees would cause chemical burns on contact. Nitrocarbonatite is intensely alkaline, and alkaline burns are serious burns, and the fine dust of cooling carbonatite is an irritant to eyes and lungs. Climbers have been caught on the mountain when conditions shifted. The approach to the crater rim is genuinely remote and genuinely demanding. What the mountain offers to those who make the pilgrimage, whether the pilgrimage is Maasai prayer or scientific expedition, is not safety. It is strangeness, and strangeness commands a certain respect. Awe and caution are not opposites. They arrive together the way they always do when something genuinely outside the ordinary presents itself without apology. What this mountain is, gathered whole, is a place where the ordinary rules of geology step aside and something stranger takes their place, where the chemistry of washing soda builds a volcano, where lava flows black and cool and turns to frost by morning, where a culture watched all of this for generations and named it correctly the house of a two-faced god, where the crater rebuilds itself in black spires and dissolves itself in rain and rebuilds again, erasing its own record, leaving no permanent stone, only the ongoing fact of its own unusual existence. It is the only one left. Every other carbonatite volcano on Earth died long ago, its sodium lava dissolved into nothing by the patient chemistry of water and time. Ol Doinyo Lengai alone remains active. Alone continues to produce the mineral that bears a president's name, and the mineral that bears a geologist's name alone goes on writing and unwriting itself in the cool air of the Gregory Rift, while the continent slowly, imperceptibly, tears itself apart beneath it.